Hello, everyone. I'm Dr. Nurul Huda, and today I will be presenting our research titled Novel 3D Printed PEGDAANF Scaffold, a Biomaterial Innovation for Soft Tissue Engineering. This study marks a significant advancement in the field of soft tissue engineering, aiming to tackle key challenges in regenerative medicine by leveraging innovative biomaterials and state-of-the-art 3D printing technology. Organ failure remains a profound global health challenge, necessitating innovative solutions beyond traditional transplantation. Tissue engineering offers a promising avenue by developing functional biological substitutes. This field fundamentally relies on the synergistic interaction of three core components: scaffolds, cells, and stimulating signals, forming what is known as the tissue engineering triad. Tissue engineering technology is designed to create biological substitutes that can repair or replace failing organs and tissues. A key principle involves designing materials that mimic the natural extracellular matrix, providing essential structural and biochemical support for cellular processes. Ultimately, these engineered constructs serve as temporary templates, guiding and supporting new tissue growth until full integration and independent function are achieved. Scaffolds are foundational to tissue engineering, providing the necessary three-dimensional environment for cell proliferation, differentiation, and subsequent tissue formation. Ideal scaffolds must possess several critical attributes, including excellent biocompatibility, robust mechanical properties to withstand physiological loads, ease of fabrication into complex geometries, and a highly porous structure to facilitate nutrient transport and waste removal. Our material selection focused on polyethylene glycol diacrylate, or PEGDA, due to its inherent biocompatibility and hydrophilicity, which are crucial for cellular integration. However, PEGDA alone exhibits insufficient mechanical strength. To overcome this limitation, we incorporated aramid nanofibers, or ANFs, to enhance structural integrity. Current challenges with nanofibers include their inherent stiffness, which can limit flexibility and biodegradability in certain applications. For scaffold fabrication, we employed digital light processing, or DLP 3D printing. This method is highly efficient, offering superior resolution, cost-effectiveness, and rapid printing speeds. However, integrating nanofibers into DLP presents challenges, particularly regarding their effect on resin curing time and overall printing parameters. Optimizing printability is essential to ensure consistent material properties and desired scaffold characteristics. Our primary objective was to develop a novel 3D printed scaffold utilizing PEGDAANF nanofiber biomaterials. We aim to enhance both the mechanical and biocompatible properties of these scaffolds through the DLP 3D printing technique, specifically for application in soft tissue engineering. Our research introduces a novel approach centered on two key pillars. First, material innovation involves engineering a PEGDA/ANF's hydrogel specifically tailored for superior tissue engineering scaffold performance. Second, process optimization focuses on leveraging DLP 3D printing to achieve precise and reproducible scaffold fabrication, ensuring consistent quality and structural integrity. A comprehensive literature review of conventional fabrication techniques revealed various methods, each with distinct advantages and disadvantages. Techniques such as solvent casting, gas foaming, phase separation, freeze drying, fiber bonding, and electrospinning have been widely explored. While some offer simplicity, others struggle with precise pore control or mechanical property limitations, highlighting the need for advanced manufacturing. Our review extended to advanced manufacturing methods, particularly additive manufacturing and photopolymerization techniques. These methods offer unprecedented control over scaffold architecture and material distribution. However, they also present limitations, such as material viscosity constraints and challenges in scaling up production, which necessitate careful consideration and further research for optimal application. Advancing hydrogel scaffolds is crucial for the future of tissue engineering. Our focus is on developing and characterizing novel hydrogel scaffolds specifically designed for biomaterial applications. These scaffolds are engineered to possess tunable properties, including porosity, stiffness, adhesion, and degradation rates, which are critical for guiding cell behavior and promoting tissue regeneration. Hydrogels are highly favored in tissue engineering for several compelling reasons. They exhibit excellent biocompatibility and hydrophilicity, crucial for cellular integration and nutrient transport. Their versatility allows for the easy formation of complex 3D structures, enabling precise scaffold architectures. Furthermore, hydrogels closely mimic native soft tissues and are biologically neutral, ensuring a stable physiological environment without acidic byproducts. Our methodology for synthesizing and characterizing aramid nanofibers involved a meticulous process, starting from bulk Kevlar to achieve a stable ANF dispersion. We employed field emission scanning electron microscopy to precisely measure the diameter of individual ANFs, confirming their nanoscale dimensions, which are critical for their reinforcing capabilities within the composite scaffold. In our mechanical property assessment, we utilized a central composite design to systematically investigate the influence of resin-to-ANF ratio and curing time on scaffold performance. The data, specifically Young's modulus values, demonstrated how these parameters critically affect the mechanical integrity of the synthesized hydrogel scaffolds, which is vital for load-bearing tissue engineering applications. Statistical analysis of the mechanical properties provided deeper insights into the scaffold's behavior. Normal probability plots and residual versus predicted value plots confirmed the validity of our experimental model. Furthermore, 3D surface and contour plots of Young's modulus clearly illustrated the optimal processing windows for achieving desired mechanical characteristics, guiding our material optimization efforts. Our in vitro biocytotoxicity study demonstrated excellent cellular compatibility of the PEGDA/ANFs hydrogels. Cell viability remained high across different printable composition ratios over 24, 48, and 72 hours, indicating the material's suitability for biological applications. This robust cellular response confirms the non-toxic nature of our developed biomaterial, a critical requirement for tissue engineering. Scaffold morphology and material characterization using field emission scanning electron microscopy and variable pressure scanning electron microscopy provided visual evidence of the scaffold's micro and nanoscale features. Observations confirmed the uniform distribution of aramid nanofibers within the PEGDA matrix, with ANF diameters ranging from 60 to 80 nanometers, indicating successful composite formation and structural integrity. In conclusion, we successfully synthesized a novel PEGDA/ANFs biomaterial, leveraging Kevlar-derived nanofibers. Optimizing the resin-to-ANFs ratio to 7:3 significantly enhanced biocompatibility, achieving 96.25% cell viability after 72 hours. The developed biomaterial was successfully 3D printed into tissue engineering scaffolds using DLP, with a 100-second curing time yielding the highest Young's modulus of 0.55 MPa, demonstrating excellent mechanical integrity. This research successfully developed a biocompatible PEGDA/ANFs 3D tissue engineering scaffold via DLP 3D printing. The novel biomaterial exhibits robust mechanical strength, with a Young's modulus of 0.55 MPa, exceeding the minimal specification for soft tissue applications. This promising candidate holds significant potential for various soft tissue engineering applications, particularly in articular cartilage regeneration,